Today, in this session, we'll be going to be talking about the lessons learned as we built a couple of reactive-based systems. I am Thiaga Manian, tech lead with Capital One, and co-presenting with me are Andy Bonham, principal engineer architect, and Raja Chattopadhyay, engineer with Capital One. So in this session, we're going to be talking about perspectives from a tech lead, an engineer, and an architect point of view of how we went about building reactive systems, especially for a credit card fulfillment system and also a card fraud authorization system. A little bit about Capital One. Our headquarters is a few miles from here, so folks who don't know much about Capital One is one of the top 10 banks in the country. We have operations in over 15 cities. We are also based out in Canada and UK. We have more than 70 million customers and 40,000 associates. As you can see, the recent awards consistently in the best companies to work for. This kind of again shows another view of where Capital One is with the other bigger banks. Based on the Q4 last year, it's in the top 10 in the outstanding loans and the deposits. So a little bit of history. Capital One is a relatively new company or a new bank. And you compare some of the banks that have been here for centuries. We went IPO in '94, so it's like 24 years since Capital One has been around. We started out as a monoline credit card company, and over the years we have diversified and grown into a diverse financial services company. And recently also transforming into a tech company that happens to be in the financial services business. As you can see, some of the recent acquisitions in the tech space. Just the background on the system that we built. So this is a credit card fulfillment system where when you go in and to like a capitalone.com site on your mobile device or your laptop, and then you apply for a card, and then once you are approved, and there are a bunch of activities that happens after you get approved. So you need to be set up in your system of record. You have to get a card in the mail, a welcome kit. You need to be set up in the rewards account. So there is a bunch of activities, fulfillment activities that need to happen once an account gets approved. So our system was to build part of this fulfillment system. And tight deadline, as everyone knows, the deadlines are always not mobile. So it was a tight deadline. This is a newly formed team. The team had 2 associates who just joined recently, and then 2 contractors. And the team did not have any reactive programming experience. So what's the mission? It was to build a fulfillment system, and we have to set up our downstream system of record once an account gets approved, an application gets approved. There are a bunch of upstream systems that we have to make API calls to get the details that are then needed to then update our backend system of record. So we could have done this in multiple ways. There was the standard way of doing this in a plain Java application. There is a Java Spring-based internal framework that is available with Capital One. We could have chosen to do that, but as a team, it decided we want to check out the reactive way of building this application. One thing to point out here is the amount of support that we got from our director and the senior leadership team on go and check it out. The only thing is like the deadline, it cannot move. Like you can try whatever you want, but we have to get this done on time. So why reactive? So this one, what we're doing was the whole modernization of our decisioning framework. So when a person applies for a card, like they say hit submit, till you get approved and you get fulfilled, we're going through a modernization and agenda. So as part of that, we want to check out if reactive would be a best fit within that. So we felt like, hey, this is a good use case that we can go and see how is reactive, how we can use it. So felt like, hey, yeah, let's go try it out. And also the way that we want to do these activities, there are like a lot of parallel calls that need to happen. And also at that point, the customer or the applicant was waiting online to get the response back. So it needs to be very responsive. Towards the kind of the middle of the project, what happened was there were some downstream constraints which kind of like moved us away from the real-time flow, whereas it was still like a real-time, whereas like it's a promise. Once the call is made, you get a response saying like, yeah, we got the request, will get fulfilled in batch at a later point of time. I'll hand it over to Andy to get a little bit more into the architecture side of Reactive.
Thanks, Thiaga. So Monolith Applications, how many folks have worked on one or maintained it? So we've all, at some point, have either had to maintain or build one in the past. What we're going to do is just touch on a couple just basic concepts that most folks in the room probably know, but just for awareness. Monolith application, there's a lot of dependencies. Again, it's where you build an application and everything is inside it. There's a lot of services that are all coupled together. They're not broken out. And over time, these things grow larger and larger. They're harder to change. And it's really hard for the engineers to keep that in their head as well. When they go to make a change to one piece, you have to think of all those other components, which leads to a lot of testing, and things are slow. Microservices, as we've heard for a number of years, they help address some of this by breaking your services into smaller pieces. They're independently deployable, so you break those dependencies between the services. In terms of size, it's really up to the use case that you're working on to figure out what's the right size. In general, you want them to do one thing and do it well. But really, you have to go through that domain-driven design exercise to figure out what your bounded contexts are and your aggregates to get to the right level. But at the same time, while microservices make the actual services simpler, it makes your overall distributed environment more complicated. So you really have to lean on your DevOps automation, your monitoring to manage that more complicated ecosystem. So in a way, it's kind of squeezing the complexity from your individual services to the broader distributed platform. Reactive architecture, when you bundle it with microservices, adds some additional benefits. How many folks here are familiar with the older approach using like an orchestrator or orchestration to do your interaction? Yeah, that's the traditional way of how you would build interaction between services, where you have one command and control component that's acting as the brain and knows what other services need to be called in what order. You can see that on the illustration on the left, where you have services A, B, and C. Now, a lot of times when that orchestration is happening, there's blocking, and blocking's bad because your total processing time is all of the services added up together. So A, B, and C, however long each one takes to run, is your overall processing time. There are some use cases where orchestration still makes sense, but the thing you want to avoid is the blocking aspect of it. And that's really the key component of what reactive architecture gets at, is how do you make your processing asynchronous? And that's what you see over here on the right with a reactive example. In this case, you do away with that central command and control orchestrator, and you distribute that logic into the individual services. So they're programmed ahead of time to know what actions to take based off the presence of data in the event stream. And in this case, what that does is it decouples them from each other. So now what they're doing is listening to an event stream like Kafka and reacting to that. You can think of it from an analogy standpoint similar to a marching band, where they're following a choreography type approach where they know ahead of time what to do when they actually go out and do their thing. The event stream itself, in this case, doesn't have any logic. It's just a place where events come and the services produce and consume from them. One of the key aspects of it is it allows you to do things in parallel. So you can asynchronously have your services run. So if service A, B, and C in this example all wanted to run based off the presence of a particular event, they could do that. Where over in the orchestrator approach, usually that orchestrator would have to call each of those three. So it's a little more resilient in that you don't have a single point of failure with the orchestrator, and things are more more decoupled. But again, the key thing you want to do with reactive is to avoid blocking. Reactive Manifesto, something that came out 4 or 5 years ago, and a group of folks came together and came up with the key pillars that they saw made up a reactive application. Responsive, so your application should always be responsive and be able to respond to clients even during failure. Resilient is how you recover from those errors and can still be responsive. Message-driven gets into the concept of asynchronous message passing, so it really gets at how you can decouple your services, and they leverage that either event stream or they're passing messages asynchronously. And then Elastic, with the cloud platforms today, it's one of the key components where you can scale up, scale down based off of the demand that's happening at the time. In terms of benefits and trade-offs, we talked a little bit about the asynchronous processing. It allows you to do more stuff and take advantage of your resources and faster response times. The other aspect with reactive is you can implement additional patterns like CQRS or event sourcing. Back pressure can also be used to allow clients to read off of that event stream at whatever rate works for them versus them getting overwhelmed with too much traffic at one time. It also helps with adding new services because in your architecture, how you've decoupled the services from each other, now they can listen to that event stream and you can add in new components or remove them without having to update as many dependencies. But as with anything, there's pros and cons. Some of the trade-offs with reactive is, it's asynchronous programming, which is a mind shift. It's not necessarily easy. I tend to think of it similar to recursion, where when you look at code that is recursive, just looking at the code won't tell you how it works. You have to think through that dimension of point in time to see what other components would be true, and that's very similar to asynchronous programming because a lot of things can be different in the environment at a particular point in time. And the other trade-off can be is if you have a really complicated use case where you're going from that orchestrator to a distributed type processing, the flow by now being distributed can be a little more complex, and that's where sometimes you might need to land in a hybrid type pattern to help for it to be the best fit for what you're trying to do. Kind of goes back to, there's not one pattern that really fits everything. There's a lot of different ways to build reactive apps. There's JavaScript libraries they can use like Angular, React. This, by the way, is nowhere near a comprehensive list. These are just some of the examples out there. There's languages that support reactive models more natively. Java 9, which is, when Java 9 came out, they introduced some native reactive features. Java 11 is the latest version there now. Scala, Clojure, some other common ones. Go, Spring 5 came out with some as well. Then there's reactive layers that run on top of the JVM. Two common ones that you'll hear in the industry are Akka and Vertex. We're going to talk a little bit more about Akka and our experience with that. Akka is based off of the actor model, which is a model that Carl Hewitt created a while back about concurrency. And what it does is it allows you, it's optional to use a supervisor hierarchy, but basically you can have parent actors that have child actors, and there's error handling that happens there. But the way the actors, they can send messages to each other, so there's a built-in messaging mechanism. You may hear of it, it's called ask and tell, where the ask is more of a kind of request response and the tell is more of a fire and forget. But actors send messages to each other through their mailbox. There's also a publish and subscribe capability with Akka Streams, where if you wanted to maybe not use that kind of point-to-point with actors, you could use that for more decoupling. Vertex is a little different. It doesn't follow a supervisor model. It's more a flat hierarchy. It does have a built-in messaging bus as well, and you can use that to communicate. Its unit of work in Vertex is known as a vertical. So we have some more info out on our Dev Exchange blog where we compare the two in a little bit more detail if you're interested. The fourth category are reactive extensions. So Microsoft came out with rx.net, and then it was in 2012, and Netflix wanted to create a version for Java, and they created rx.java. And one of the cool things with a lot of these is they're built off of the reactive stream spec, which basically means you can use them together. They're interoperable. So a lot of times you'll see Vertex or Akka and Java RX used together in a project because folks are trying to optimize for the things that each one does well and use them together in a project. Now I'll hand it over to Raja, who will walk through the Akka use case.
Thanks, Andy. Okay, so now we'll talk about the project where we implemented the Akka. So we started with the fulfillment process, as Thiaga mentioned, and then there was another use case for correspondence. I'll talk on those things later in a different slide. But the main technology that we used in our project is extensively Akka framework. And it's not a framework, it's more of a toolkit. And there is a framework called Legume. It's like developing the Akka using the Legume framework. So I'll talk a little bit more on Legume as well. We extensively used the Java completable feature interface and a little bit of Akka cluster sorting. Moving on, so Legume is a framework to create the reactive-based microservices. So sometimes developing reactive-based microservice can be hard. And what Legume offers is simplifies those complexities, and it's run on top of event-driven programming model. So with Legume, we started creating a few POCs, and it was really quick. And then we decided to leverage the Legume framework when we started building our microservices based on reactive framework. So what Legume offers, let's say you want to use Kafka and Cassandra in your development environment. So it's more of one single command, right? And it'll be up and running. Your code can be integrated within few lines of code with Akka and Cassandra. And so in that way, right, even if you want to integrate Akka or Cassandra or some, you want to create some API, it's really easy. It can save a lot of time if you are developing a reactive-based microservice. Later also, we created the CQRS pattern with Legume framework, and it was also very, it saved us a lot of time. Moving on, this is the first project that we did. So as Thiaga was mentioning, during the fulfillment process, what we wanted to use is more of an asynchronous mechanism, right? So we receive a feed or request, right? And it will be accepted by our REST API, which is developed using Akka. And immediately we return back an acknowledgement. So it's like fire and forget pattern. We receive it, we are not blocking that thread. And then what internally we do is it will be received by an actor eventually, and then the actor will start calling bunch of APIs. But those calls will be more of an actor-to-actor communication. It's not in direct, the main actor to that API. It will be via an actor, and then if you think about the Saga actor is the main actor here, and let's say if I want to call that app capture, details API. What I'll do is that I'll make a call to app capture actor, and app capture actor, interns will make a call to app capture API. So internally, the communication is like actor to actor, and finally, an actor will make a call to the outgoing call. In this way, right, what happened is that within our use case, there are a couple of API calls. Those were like asynchronous. And there were a couple of API which were more often synchronous in nature. But every call, whether it's an asynchronous or synchronous, was non-blocking. And internally, Akka was managing those calls. We didn't have to do anything to write anything for non-blocking code. It's already taken care by the Akka framework. Now, during that process, right, it can happen that one of the API is facing some issues, some network cliff, right? It can happen. It's a real scenario. Now, what we did is we created a different instance of Postgres, and we maintained the status there. And there was a different application called retry, which picks all the information from that Postgres instance and reposts it into the REST API one more time. Now, this is not the Akka way of doing it. Akka way of doing is more often using the persistent mechanism, which we leverage in our next project. So I'll explain that part as well. Moving on, the key capabilities of this fulfillment process was receive and validate the request first, and once that is done, we call a bunch of APIs, mainly asynchronous and both asynchronous and synchronous way. And once that is done, we update the system of record. Because there is a legal part associated with that. In a sense, once we save that information in an app data store, that was used by the legal compliance team. Because there was some date, and it was like a hard date for us, and we had to finish our job before that date. Also, what we did is during this process, we registered every event in a different store called registry. From a resiliency point of view, Akka actor system itself is a very resilient. If something happened, it can come back from the previous state. And then you can have the supervisor mechanism. If something happened to your child, you can control what needs to be done. You can say, hey, restart, and go to your previous state. Or you can say that, hey, stop, I don't want you to be run anymore. Another thing that we faced is, let me go back to the previous slide. See, the way that we were receiving the request and the TPS requirement was different from the upstream and downstream point of view. Akka is a high-performing system. It doesn't block anything. But that was not the case for the downstream API. So we had to manage, and we had to create some throttling mechanism. So that we build as part of this project as well. Okay, so the main lessons that we learned during this project were Akka is, takes time to learn Akka. It's not that easy. Unit testing and performance, initially we faced few issues, but in later project it was all good because maybe we were familiar at that point of time. Initially it took a little bit of time to do that unit testing and performance testing. Akka is a high-performing system, but we had to do that throttling mechanism, and that was limiting the Akka performance. We dropped few key features of Akka, like Akka persistence and Akka clustering. But in our next project, we leverage the Akka persistence, and I will explain it now on the correspondence use case. Now, this is the use case. Let's say a user is applying for a credit card. The outcome could be approved or declined, right? But in both the scenario, from a legal point of view, we are bound to send a letter or communication to that end user, right? So correspondence does that, the functionality. We receive a request, and with that request, we got in status whether the application is approved or declined. And what we do here is we go back to the application detail API, get all the application details, and then make a call to the send letter API, which is more of a third-party API for us right now, who does the printing and send that later to that end user. But what we did as part of this project is when we receive a request, we create an event. We leverage the CQRS pattern, and we write all the logs in the write side. But in the read side, it was maintaining the state of that application, right? So you can have a couple of deltas as part of your update, and each delta is actually going there in the right side, but read side is maintaining the final status. So at a particular time, if you want to see what's my status of that application, I can very well query my read side and get that status. However, if I want to see, hey, what happened to this application? So I can retrieve all the events from my right side and return back the event history to the end user, and based on requirement. So these are all the key capabilities that we fulfilled during that project. And one more interesting thing was like restart the service call from last failure. What does it mean is, let's say if I'm making a call to app details API, that was successful, but when I'm making a call to send letter API, that was failed. Now I need to retry it, but do I need to go back to app details API one more time? No, right? It's already there. It was successful. Why do I need to go there? So Akka persistence helped in that context. So if you want to retry, it can reinstantiate to your previous state. And then from there, you can figure out what's your failure state and make a call to that API. Yeah, so with this, I'll hand it over to Andy.
Thanks, Raja. So what we wanted to do next was talk a little bit about how you can integrate some of these patterns with machine learning. As everyone knows, machine learning is pretty awesome. It's a hot area right now. This slide shows you, and we do have a demo that we'll show you here. Looks like we're doing okay on time, that we built that shows some of this. So this slide shows you the history in general of artificial intelligence, machine learning. It's actually been around for a while, came out in the 1950s. A lot of the systems then were known as expert systems, and that's where humans had to write in the if-then logic, so it was kind of the early form of rules. Then in the 1980s, we started to see some of the initial versions of machine learning. Has anyone seen the movie? It's kind of an older movie, Short Circuit, with Johnny Five. Yeah, so in there, kind of showing my age on that one. In there, there's an episode where, or a scenario where Johnny Five takes, I think it's like an English dictionary or the encyclopedia, basically reads through the entire thing in 30 seconds. So in a way, that was kind of an early form of machine learning in Hollywood. But neural networks is how things started there. A lot of the software that was there was commercial. There really wasn't any open source. And it also wasn't exactly easy to deploy. Where now the shift into deep learning, some examples with self-driving cars and image recognition gets more into that deeper neural networks that mimic the sensory in the human brain. And then two high-level categories. There's more categories in between these two, but in general, you have supervised machine learning and unsupervised. Supervised is where your data is labeled and you provide a target, which is the thing that you want to predict, and you provide all the features for an algorithm to run through, and it basically figures out, okay, out of the data you've provided, what are the ways to predict the target. And then unsupervised is where you don't provide the target, rather you give it the data, it then classifies it and categorizes it and figures out how it's related and can be used for predicting. So when you start to think about this and how you can apply it to a reactive type concept, these are some different patterns we've thought of. We have a couple experiments we've done internally around human workflow, so open source EPM. In this case, this example is showing the JBPM open source project. Here it's called PAM, which is what the newer version is called, Process Automation Manager. But in this case, it's following a reactive integration pattern with Kafka. And then we have separate microservices that are calculating features. And we're also leveraging H2O in this example that we'll show you, which is an open source Apache 2 library you can use to build supervised and unsupervised models. One of the cool things about it is once you build your model, you can deploy it as a POJO, which makes it pretty easy to integrate into a Java microservice. You can also use it, there's a different format it has called a Mojo, which is a model object deployment, which you would use if the POJO gets larger than a certain size and has a little better performance. And then there's different flavors you can do where if maybe you didn't want it as decoupled, you could build it all native inside the open source BPM tool. Then there's ways you can do this with Akka as well, right? Where you can wrap the microservices with Akka actors, have them communicate with each other, and then also the Kafka event stream. And typically the way you see actor systems integrate with each other is through Kafka. So in this example, you could take what Raja talked about with the correspondence actor system, and you can integrate that with another actor system that's maybe running models. So this is another way of many of how you could do this. What we'll do now is show you a quick demo of the pattern on the far left, where JBPM is interacting with Kafka and several microservices. We have these right now all in different Docker containers, but we're not using a container management solution right now for this example, but we'll walk through, show this to you guys here real quick. So these are, we'll switch over. Might have to go back. All right, so these are the two EC2 instances that we have running in AWS. One's running the JBPM Docker container. Another is running 4 different Docker containers, including Kafka. So we'll go over here. So this is the one running. Just bear with me here real quick. Make sure we're still connected. Lost our connection. That's all right. All right, so you can see there's our Docker container running JBPM. And if we go over to our other instance, what's the connection on that one too? And these are the 4 other Docker containers. One's running the run model microservice that has a H2O POJO we created. So what we did is we took there's a data set open source site out there called Kaggle that you can leverage data sets for. So we took a sample data set that's simulating credit card transactions, and they have about I think 300,000 rows in it. And what it does is basically they anonymized, sorry, I'm shutting this down. They anonymized about 28 features. So there's 28 numerical features in there. You don't know what they are because they didn't want to release that, but there's 28 features, and then there's a target column that tells you if the transaction's fraudulent or not. They also provide a transaction amount and the time. So what we did is simulated running data like that through that model. And when we built it initially, we experimented with a couple different algorithms. We first used the gradient boosting machine, and it didn't work. The stats on it weren't very performant. Then we tried the distributed random forest, it had a lot better prediction. I'll show you guys our GitHub repo here in a minute. It actually has both POJOs in there. The one that's connected to the service is the distributed random forest. So what we'll do is go back here, and what I'll do is just open a quick Kafka console through here. So what this is doing is connecting to our Kafka topic, and you can see we've been running some tests in here to make sure the demo would work when we show it to you guys. These are events that the microservices are reactively publishing to Kafka along with JBPM. So what we'll do is leave this up as so we can see what things are writing to it. Then if we go over to JBPM, this is our business process that we are going to execute. And we use a little bit of a hybrid pattern here where this is a little bit more than human workflow. It's a little bit of orchestration. You can call it more coordination, but what it's doing is it's reactively listening to Kafka and then driving a flow. So what we do is we have a event that we simulate onto the Kafka instance that says, hey, I received a transaction. And then what it'll do is it'll actually write a command back to Kafka. That's a typical concept you'll see in reactive patterns is you have commands and events. Commands are things that you want something to do. Events are things that have happened in the past. So what this will do is this will actually publish a command that says, hey, go calculate some features, or calculate microservice right here. We'll see that event, execute, publish its result as an event back to Kafka. And then the run model microservice will see that, execute, and then publish back. And then when we go back to JBPM, it's actually listening for the output of that H2O model, where it'll say, okay, if the output is okay, we're done. If it's fraudulent, do some more stuff. And we kind of just left this as a open-ended thing where it'll write a final message, but you could, integrate some human workflow at this point or call, trigger some other events. So what we'll do is show you this here real quick. So we're going to flip back to this when we actually run it. And we'll flip over. This is already built, so we'll execute this kickoff service. And if we flip back here, there we go. So it already executed. So transaction received. JBPM read it, wrote the calculate features, and here you can see all of the 28 numerical features coming back, the amount, and then our model ran. You can see here H2O outputs a P label. 0 means it's false, so that's why it wrote transaction okay, and it gives you a probability. If we run another one through here, see if we can get a fraudulent one. Okay as well. Let's try one more time. Here we go. So that one came back fraudulent. So you can see the P label of 1 there. And then if you wanted to go and see the flow that it actually took through the workflow, you can go in here and it'll show you. So the path that is grayed out is the path that it took. So that first one we ran, it said transaction was okay, so that's why it's grayed out there. So anyway, this is just a pattern, bit of an experiment, but a couple pieces of this pattern we've integrated into some components. Here's the GitHub repo if you guys want to check it out. It's got all the components in there. I think that's it. I'll open it up. What questions do you guys have? You guys want? The question was, how did you decide about using a short-lived or long-lived actor in the actor lifecycle?
So this one was, since we had the persistence using Postgres, right, so it is pretty much like a short-lived actor. So if there was a call to an API, which is down, we basically persist to our Postgres, and then we retry it. So that's kind of the pattern that we do.
How did you handle the distributed transaction across multiple actors and multiple APIs?
So in this case, at least our use case was slightly easier in the sense, like we could retry it again, so it is won't cause any side effects. So if it was like stuck at step 5, we could rerun from steps 1 through 5 without any issue. So at least in our use case, like we didn't have to, but you could persist that state information, and then you can continue from that step on.
So, but what you're saying in the Akka persistence, so have a state stored and then replay.
Yeah.
Or you can use the cluster, Akka cluster.
How about if my actor decides it's a business problem, I fail, I want others to notify again, right? So in the scenario, you again put it in the same actor system again. Is it something you...
No, in this case, it was more like retry. So there is a retry mechanism, tries multiple times. Like we have a track count.
It's a valid reason, business reason. It's not a system failure or something like that.
Right.
In this scenario, I want, like, there's an actor, another actor.
Right.
This failed. Should we go back and tell the other actors to...
Yeah, if it's a business, then it should be a normal exception, normal business.
Normal business.
Yeah.